thank the organizers for inviting me to come speak today. And in my title, I promised a lot of things, and then when I started to put the talk together, I realized I couldn't fit them all in. So I've cut down the scope of the talk, and I'm going to mainly focus on what I'm going to call the plate tectonic approximation after 50 years. And the part of the title, let's see, is that okay, that works. I promised to talk about Cenozoic, true polar wander, and the origin of the Hawaiian Emperor Ben. I'll be talking about that at the fall AGU. Sorry, there's just not enough time for me to do it all today. I'll be talking work that I've had many collaborators, most of whom I've listed here are full partners in all the research that I'm going to be talking about. So let me give you a summary of what I'm going to say. It's a long summary, 20 minutes worth. So plate tectonics originally assumed narrow plate boundaries, as we've heard today, but we now recognize that many of these boundaries are wide, or you might call them diffuse, as wide as 1,000 kilometers across or more, instead of the few kilometers in the original plate tectonic model. And what I would call diffuse plate boundaries in the continents were recognized early by many workers, including several people present here today. But they were recognized later in the oceans, and my colleagues and students and I have had done some of this work to recognize them. So the diffuse plate boundaries, instead of having narrow plate boundaries over the whole Earth's surface, cover 10 to 15% of Earth's surface. And so instead of the world being covered by a mosaic of rigid plates, that applies to about 85% of the world, and the other 15% of the world are these broad deforming zones that constitute the diffuse or wide boundaries between some of the plates. An outstanding example of a diffuse oceanic plate boundary is the boundary between the India, Capricorn, and Australia plates that I'll talk about in this talk. Poles of the rotations of the diffuse oceanic plate boundaries tend to lie in their mutual boundary. And we don't see this for the typical narrow boundary, so it's a different phenomenology, and it's now understood to be a consequence of both plate geometry and rheology. When we have a broad zone of deforming oceanic lithosphere, it can be modeled as a thin sheet of viscous fluid. If it's a power law fluid, the best fitting power law exponent is about 30, and that's a lot bigger than the typical estimate that's come up with for continental deforming zones, which are often quoted as being from power law exponents of 3 to 5. So the wide plate boundaries are kind of the first topic I'm going to hit. The second one is plate rigidity. So if we exclude all these wide deforming zones, especially if we focus on the oceans, what's left should be rigid plates. But rigidity has always been an approximation, although it's a very excellent approximation, but we have tried to work to see exactly the rates at which the plates deform, how non-rigid are the plates. And two of the important processes, that the Earth is not a perfect sphere, and also thermal contraction, were recognized early on, and we have elaborated on this work. One of the consequences, surprisingly, is although one of the corollaries of rigid plates is that the transform fault should be exactly parallel to plate motion, we think there's actually small deviations of about 1/2 degree, and that's due to the fact that you have horizontal thermal contraction of oceanic lithosphere, especially young oceanic lithosphere. Space geodesy quantifies significant short-term non-rigidity due to glaciation, which I think was already mentioned in Jason's talk. A current challenge to the rigid plate hypothesis, a phenomenon we don't understand, is just that when we sum up the plate circuits around the Galapagos Triple Junction in the Pacific, we have 15 plus or minus 4 millimeters of non-closure. It's a huge amount by plate tectonic measures. Okay, finally, I'm going to talk a little bit about space geodesy, mostly in the context of what the steadiness of plate motion is. So space geodesy, of course, allows us to include plates that are not bounded by mid-ocean ridges, allows us to analyze distributed deformation on the continent, such as the Basin and Range province in North America, the San Andreas Fault System in California, other distributed deformation. And we find that plate motion is mainly steady, also as demonstrated in Jason's talk, but there are some significant differences between geologic and geodetic rates, and I'll show those near the end of the talk. Okay. All right, but before I get into the heart of the talk, I missed the plate tectonic revolution. During 1960 to 1968, I was in elementary school and middle school. And as a university student, I didn't take any earth science until my third year as an undergrad. And so that was in the fall of 1973. And the textbook, even in 1973, did not have the word plate tectonics in it. However, the instructor who'd gotten his PhD in Princeton was on top of plate tectonics. Also required us to read several Scientific American offprints, which talked about seafloor spreading, but really didn't give us the whole plate tectonic theory. But in that same academic year, in the spring of 1974, I took a course in marine geophysics, and we used this is Xavier's book, which had been out for less than a year, and I read that cover to cover, and that's my introduction to plate tectonics. Thank you, Xavier, for writing that book. Otherwise, I would not be here, I don't think. And soon after that, I decided to switch my major from physics to earth science. So thank you, Xavier. All right, the original tenets of plate tectonics, and I'm interpreting explicitly that the boundaries were narrow, certainly in Tuzo Wilson's original paper, and that the plates are rigid. Also implicit, I don't think it was ever stated in those early papers, is that plate motion is steady, but it was implicit because the early workers used the earthquake focal mechanisms interchangeably with more or less with the transform faults. And so there was this implicit thing that what we see today is the same as, in a human time scale, is the same thing that we see over a geologic time scale. So we're going to look at these three original tenets in a little bit more detail. So this is an updated version of I took a world plate boundary map and then sketched on the diffuse plate boundaries quite a long time ago to get across the idea of the diffuse boundaries. Of course, in the continents, a broad region in Western North America, a broad region here in the India-Eurasia collision. If the East Africa Rift is a plate boundary, it leads to a broad region. You also have a big region of deformation here in the South America Cordillera on the two sides of the Andes, but it's not just in the continents. Recognized early on, I think Ball and Harrison wrote the first paper about it, there has to be some kind of zone of distributed deformation between North America and South America. Still, if you look in the textbooks, at least the introductory textbooks, every plate boundary map shows a little line here between North and South America, and that's what we're still teaching our introductory students, at least in the US, but the line does not exist. There is no narrow plate boundary there. It's a broad region of distributed deformation. Also in the oceans, the outstanding example is here in the Indian Ocean. I've shown them as disconnected regions, but there's a broad deforming region here that's accommodating, in the oceans, that's accommodating the relative motion of India, what we call the Capricorn plate, and the Australia plate right here. And this is a big zone of horizontal contraction. It's a profound fold-in thrust belt. Living in Texas, my frame of reference for Texas is the size of Texas, because we ignore Alaska and we think that Texas is the biggest state. Texas is roughly the same size as France, more or less, and you can fit 12 of Texas into this deforming zone. That's how big it is. Or you can fit, if you, once again, leave out Alaska, you can fit in all the United States. That's about the same area as this contractional deforming zone here in the Indian Ocean. Okay, so I think I've got another. So here's zooming in a little bit more on Indo-Australia. So once again, traditionally, this has been assumed to be a single plate, and at least in the original plate tectonics, the Indo-Australia plate. We now recognize it as 4 plates plus the intervening mutual diffuse plate boundary. So I mentioned India here, Capricorn, it's all oceanic here, Australia here, and a Macquarie plate down here. So I've tried to call this composite of all of them a composite plate, but that's actually a bad name in hindsight because it's not a plate at all. It's 4 plates plus some plate boundaries. So maybe it's better to call a plate composite. But it's still nice to have some this tightly coupled mechanical entity to have some kind of name, and maybe someone in here will come up with an even better name that will catch on to describe what Indo-Australia is. But it's not a plate, it's 4 different plates. Okay, if we look at the poles of rotation here, this is the location of the pole of rotation between the India and the Capricorn plate. So generally speaking, if we look at poles of rotation, like those found by Dan McKenzie, Jason Morgan, Xavier Lapuchon in the early work, the poles of rotation are mathematical conveniences for describing the relative motions between 2 plates, and they lie far away from the mutual boundary of the 2 plates. They never lie within the boundary. But in these diffuse oceanic plate boundaries, there are a number of examples where the pole of rotation lies within the boundary. So one of those examples is India relative to Capricorn. There's that pole of rotation. So it means that there's a kind of a physical or geological interpretation that goes with the pole of rotation since it lies in the plate boundary. In this case, if we hold Capricorn fixed, we have a left-handed rotation of India about that pole of rotation. So that means that India and Capricorn are converging over here, but on the other side of the pole of rotation, they're diverging. We're getting horizontal extension. Similarly, we think the pole of rotation between Capricorn and Australia lies right about here. Once again, if we arbitrarily hold Australia fixed, then Capricorn is rotating with a left-handed rotation so that we get convergence across here, and then we get extension over here. And then if we sum those 2 rotations up, we get the rotation between India and Australia. That pole of rotation is sitting somewhere over there. And so they're just converging across a very broad diffuse plate boundary that merges into the India-Capricorn and Capricorn-Australia convergent boundaries. So another place where we think the pole of rotation is between the plates is in the boundary is here between Macquarie and Australia. Another example is between North America and South America. Another example is between Nubia or West Africa versus Somalia and East Africa. In each of these cases, the pole of rotation. And so we think that has some information about the physics of the processes, and part of that information is across those boundaries, the plates are much more tightly coupled than across the narrow boundaries, which are relatively low in stress and force per unit length in terms of the coupling than on these kinds of boundaries, except some of the subductions, the trench boundaries, which are, but not all of them, that are tightly coupled. Okay, so I want to talk a little bit about some physical modeling I've done with Greg Hausman to describe the deformation that's going on in this diffuse plate boundary here between the India, Capricorn, and Australia plates. We're trying to model the deformation across here and over here. So we're building on work that Greg and his colleagues, including Philip Engelman, have developed a formulation in which we use a thin viscous sheet model, which was originally applied for continental deformation, but we think it works at least as well for these regions of diffuse oceanic deformation. So the horizontal stress is balanced within a thin spherical sheet, a finite element formulation based on a triangular mesh, a plane stress formulation. The buoyancy forces due to variations in deformation-induced thickening are assumed negligible in the continents, where you have buoyant continental crust in contrast with the mantle. You have to account for these buoyancy variations, but in the oceans, the crust is thin and the density difference from the mantle is so small that we think that we can neglect these. The deformation rates obey a power law rheology, where this is a component of stress, this is a component of strain rate, E is the second invariant of the strain rate tensor, and N is the power law exponent. So current displacement rate and strain rate fields are calculated. So, so the reason that we did the domain of the finite element calculation is outlined by red right here. So we've included all of the India plate, all of the Capricorn plate, and part of the Australia plate. We don't need the rest of Australian plate, which we're just considering to be rigid for our purposes, to do this calculation, and we also include the intervening deforming zones. And this is just to show you the earthquakes that are in in the region. White are mainly normal faulting mechanisms. Black are mainly thrust fault mechanisms. And red are mainly strike slip mechanisms. And the larger the moment magnitude, the bigger the symbol here. Okay, and then to do our analysis, we use kinematic boundary conditions because we don't know all the forces along the edges very well. We do know the relative motions pretty well, and we use the relative motions from the Moravelle set of angular velocities, relative angular plate velocities. So, so once again, here's the domain for our analysis. So India is over here, Australia is over here. You see the same shape represented over here, and this is how we applied the boundary conditions. This part of the outline, which is kind of a purpley blue outline, we applied, we forced it to take on the motions of India in a reference frame which is halfway between India's motion and Australia's motion. This part that's kind of pink, we forced to take on the motions of Australia, and this part here we forced it to take on the motions of the Capricorn plate. And in between these regions, we just tapered smoothly from one to the other. So these are basically interpolated with some smoothing across these zones. So that gives rise to the set of velocities that we see on this diagram with India rotating to the east here and Australia rotating more to the north. Their mutual polar rotation is somewhere over here, but Capricorn's motion is specified independently of that. So this leads to this set of strains for 5 different numerical experiments. And so everything is the same in these experiments except for one thing. We've only changed one parameter, and that's what we assume for the exponent for the power law for the fluid. So n equals 1 is just an ordinary Newtonian fluid, and then these are all non-Newtonian values. N equals 3, n equals 10, n equals 30, n equals 100. The value n equals 3 has been found in several cases to be a good fit to continental deformation. I won't go through the whole set of criteria we use to evaluate these, but as you can see quite qualitatively, so these are contours of strain rate, contours of vertical strain, so that this is where we have thickening at red, and the blue or green are going to be thinning. So we're getting extension here between India and Capricorn, and we're getting extension here between Capricorn and Australia, and we're getting convergence here. But here you can see it's very diffuse at n equals 1. At n equals 3, it's very diffuse. It starts to sharpen up at n equals 10, becomes even sharper at n equals 30, and then very sharp at n equals 100. And if we actually look at the locations of the earthquakes, which is only one of many deformation indicators, ways of measuring the distribution of deformation, there seems to be a zone of deformation here, and then it connects over possibly, or a separate zone of deformation over here. So if we don't see these two distinct fingers, it's really not a very good model. So applying some quantitative tests, we determined that n equals 30 was the clear best fit. We're pretty sure we can reject 1, 3, and 10, and 100. So the best fit to the observation comes in when we use a power law exponent of about 30. So, oops, oh, what did that do? That didn't look good. This one, okay. So this, in the preferred model, n equals 30, this is a map of strain rate on the left using the second invariant of the strain rate tensor. And you can see, although the contours are maybe a little offset from the earthquakes, it really matches the distribution of the earthquakes pretty well. I mean, I won't go into the details of it. With just those boundary conditions, we matched the distribution of the earthquakes, but not the focal mechanisms. We had to introduce one other additional parameter I won't go into today in order to match the actual focal mechanisms, which are illustrated over here. But once again, right, we have normal faulting, a mix of strike slip and thrust faulting here, and normal faulting down here. And obviously, our model doesn't explain these earthquakes pair at all, since we're treating that part of India as nearly rigid. Okay, so that's the time I'm going to spend talking about diffuse plate boundaries and diffuse oceanic plate boundaries. And I want to turn to the subject of plate rigidity right now. So the central, there were those three tenets I listed at the beginning of the talk, but really the central tenet of plate tectonics is that the plates are rigid. So even when we have these big, broad, diffuse oceanic plate boundaries, we can still apply plate tectonics to make predictions about what's the integral of the deformation across them. So as long as you've got a rigid core to the plate, even if the boundaries aren't narrow, plate tectonics still helps you. Plate tectonics is useful. So, but what about those parts that we've assumed are rigid so far? No real material is rigid. How close do we come to that? So how fast do the questions we're interested in is how fast do they deform or strain? How do these strain rates compare with those in diffuse plate boundaries? Compare with those within narrow plate boundaries? How is straining distributed spatially? What are the main processes by which they deform? So, and there is some evidence from using plate tectonics, we can test this central assumption, are the plates rigid? And there is some evidence from plate motion circuits for sort of geologically current motion, the motion over the past 1 to 3 million years. The plates look like they're not quite rigid. If we go North America, Nubia, Antarctic, Pacific plate circuit, and then compare it with GPS, so there's a lot of assumptions involved here, we get a misfit of about 5 plus or minus 3 millimeters a year. Around the Bouvet triple junction, we get a significant misfit. It's small, 3 plus or minus 2. It's actually 2.5 or something. I mean, but around the Galapagos triple junction for the Pacific, Nazca, and Cocos plates, we get this astounding misfit of 14 plus or minus 5 millimeters a year. We do not understand it. If this is right and we're not missing any plate boundaries and the plates aren't very rigid at all, I don't think that's right. We're still missing something we don't understand. We've done some more work to try to improve this data set. We think we could trim this down to maybe 11 plus or minus 5 millimeters a year, but we can't make it go to 0. It's too large to explain by known processes of interplate deformation. I think I have it illustrated. Okay, I have it coming up on another slide. So let's take a quick look. The specific North America plate circuit test, we reference it to a spot along the San Andreas Fault so we can compare the velocities. But basically, we go Pacific to Antarctica, Antarctica to Nubia, Nubia to North America, and then we compare it with what's observed with GPS, and they don't match. They're outside the confidence limits. This is the one for Nouvelle 1. This is the one for Morville, where we're summing up the best fitting angular velocities, which is analogous to what we'd be doing if we wanted to get the relative motions 10 or 20 million years ago in a plate circuit. So that difference appears to be statistically significant. Okay, and then once again, just to illustrate this, here's the Cocos plate, the Pacific plate, the Nazca plate. We can evaluate these velocities, their relative velocities near the Galapagos triple junction here, where the three plates nearly meet, except for the microplate that's there. So if we start at the Cocos and go over to the Pacific, we get this. Then Pacific to Nazca, and sum up the errors, we get this. The Nazca back to Cocos, we wind up here, not here. So these differ by about 15 millimeters a year. It's a huge misfit. The main explanation I can think of is staring in front of us is a plate boundary we're not seeing. It's so big, but nowhere within these plates are there earthquakes big enough that you could, to argue for a plate boundary. So it's a bit of a paradox right now. And certainly it's not the Pacific plate. And so the most likely one would be the Cocos, splitting it into two because it requires the least amount of slip rate or deformation rate to account for it. But we're still puzzling this one out. Okay, so the plates aren't rigid. So what could cause the non-rigidity? Two possibilities we've explored is plate movement over non-spherical Earth, first proposed by McKenzie and then by Turcotte and Oxborough. I won't go into any more on that today. Another one we've explored is horizontal thermal contraction of oceanic lithosphere, first proposed by Colette, and we've done some work on this. I'm going to talk about that in the next few slides. So we all know that the the seafloor subsides with age, and that's due to thermal contraction. But it's also contracting in the two horizontal directions, but those effects are much harder to observe. Some simple calculations show you that the rate of that shrinking in the horizontal direction is roughly infinitely proportional to the age of the lithosphere. So it drops off really fast with age, faster than the heat flow, faster than, and faster than the depth-age relationship. And then we have to put a little fudge factor here because at zero age, the lithosphere is not zero thickness. We know it's something between 2 to 7 kilometers, depending on the age of the lithosphere. All right, so we did some calculations to get these strain rates, and they can be quite high, especially for the young oceanic, whoops, I did it again. Young oceanic lithosphere. This is some work I did with Corné Kramer, where we tried to put in that relationship with the age, and then use the programs developed by Haynes and Holt in order to enforce strain compatibility across the whole thing so that we deform a plate without opening up holes or building mountains or anything like this. And so this is the Pacific plate. Okay, and so we're showing contours of the log of the second invariant of the strain rate tensor. So the sheet rates and the variation of the strain, I think so, it's expressed in terms of strain per year over here. Very high rates along the newly created seafloor, drastically lower rates in the old seafloor. And so these are two different realizations. We have a parameter that we can dial, and so we took it to the two extremes. On the left, we optimized to match the expected aerial changes predicted by that relationship I showed in the last slide. On the right, it's optimized to preserve shape. So on the right, we've tried as much as possible to keep circles as they shrink. Over here, we've tried to match the shrink rate to the age of the lithosphere as closely as possible. So we get patterns that are different, but still broadly similar in that you have very high rates near the ridge, and then orders of magnitude lower out in the old seafloor. So when we integrate either one of these to get a velocity field, integration smooths over the differences. They look visually almost the same. And so here is an example of one of these. In this case here, we've minimized the motions of some of the GPS sites on the oldest lithosphere in the Pacific, which is probably the part that's not deforming. And then that lets us look at how fast the lithosphere, at the other edge of the plate is moving. And you can see this light green contour here is between 1.5 and 2 millimeters a year. So we get between 1.5 and 2 millimeters a year. Here we use a different reference frame. We took an isochron near the Pacific-Antarctic rise, which you would go through in a plate motion circuit. And so we minimize the motions of sites along it. And when we do that, we get faster velocities because this frame, it's the same strains, just one frame is rotating relative to the other. And here we cross the kilometer. This is the 2 kilometer contour, so we're up into 2.5, almost 3 millimeters a year as we move along the North American coast of the Pacific Plate, just from the expected thermal contraction. Okay, so how can we further test the predictions of this shrinking plate hypothesis just to contrast it with the rigid plate hypothesis or approximation? Well, we've heard about how GPS is transforming how we look at deformation on the continents, but there just simply aren't enough islands in the oceans to get a dense network, and a lot of times the islands are in the wrong places to test this because the biggest effects are in really young lithosphere. So there's really no way I see to test anytime soon this model with GPS data. But it turns out that when we calculate the azimuths of the transform faults, it predicts they should be slightly non-parallel to the direction of plate motion, and we have lots of good measurements. We can do statistics on them to see whether or not we see this in the transform faults. So I'm going to just show you one example. This upper diagram here is from a paper that I wrote with Jay Mishra. We looked at the 6 plate pairs that have both right slipping transform faults and left lateral slipping transform faults, or have enough of them that have both. So in each case, and then we found the best fit to plate motion that is a compromise to all the transform faults, and then we looked at the residuals and then broke them out by right lateral and left lateral. And so I haven't really emphasized this yet, but the shrinking plate predicts that you have a different sign of the effect for left slipping faults than you do for right slipping faults. So here, the left lateral slipping faults are the red triangles, and the right lateral slipping faults are the blue circles. These are the transform fault azimuths right out of Morvell, so that we're looking for a small effect, so we don't want to let investigator bias get involved in this. And if we take the mean of the left lateral and the mean of the right lateral for each of these 6 cases, in each case, the left lateral is clockwise of the right lateral, as we would predict. And we have other quantitative ways of investigating it, but on average, on the planet, the size of the offset matches the predictions pretty closely. So this shows, I mean, it's a prediction of the plates not being rigid, a specific process by which they're not rigid, makes a specific prediction for the transform fault data, and shows that the prediction is converged. And the chance of doing this, for example, accidentally, in 6 out of 6 cases is 1 in 64, and there's other ways we can quantify the uncertainties here. But it seems to be significant at, our usual 5% significance level, 95% confidence level that we care about. Okay, so talking about non-rigidity further, Jason actually also mentioned this too. This is some work I did with Don Argus. Actually, Don did most of the work, in which we're looking at various types of space geodetic sites on North America, not just GPS, but also satellite laser ranging, VLBI, and so on. And as Jason pointed out, okay, we have the swath here of sites that are black, and those are what we use to estimate the motion, to define the stable interior of North America, and we don't see any resolvable motion between those sites. In the west, with the blue sites, are sites that are in the broad deforming zone here between the Pacific plate and the North America plate, which you could argue in somewhere here near Denver, as long as you stay east of the Rockies. But here, Platteville is an example of this, but when we get into Ely, Nevada, for example, 5 millimeters a year, we didn't even put in the Sierras and near the San Andreas, which are much higher rates. Okay, and then next, we had to exclude all the sites shown in red because the expected post-glacial rebound horizontal velocities are so large that it would corrupt the reference frame. And so, in fact, if we look at this in terms of strain rates, these strain rates are similar to the ones that we see in diffuse continental plate boundaries. And sort of a strain rate comparison is in this diagram here. Okay, so I hope that's not the signal that I'm out of time. But so narrow plate boundaries have really high strain rates. Here I'm putting them kind of geologic strain rates. So this would be 10 to the 1, 10 squared. So this is a strain rate not of 100%, but of 100 per million year. Narrow plate boundaries have really high strain rates. If we want to look at the strain rates in a diffuse continental plate boundary, like the deforming zone between India and Eurasia average across it, that's orders of magnitude lower. That's right about here. If we look at diffuse oceanic plate boundaries, the peak rates are about an order of magnitude lower than the peak rates in the continental boundaries. So the strain rates are lower, the material properties are different, but because they include the poles of rotations, the strain rates drop down to vanishingly small values. For the oceanic thermal contraction, it can even be higher than we see in the diffuse oceanic plate boundaries, but that only applies over a small strip of seafloor, the youngest seafloor, and it quickly drops down to lower than this as we get an older seafloor. We've done some calculations to try to quantify non-sphericity, and it comes out a little bit lower than those two values, but we're still working on this. Maybe this number will get bigger in our next calculation. And these are just simply bounds on what's the strain rates in stable plate interiors. We don't know what they are. We know that they're bigger than sort of the moment release from the earthquakes that occur in stable plate interiors, and they're smaller than the upper bound we can put on from space geodesy. It might be in the lower end of this range. here. But anyways, these things break out pretty cleanly when we look at them in terms of strain rates. It's plainly in the sense that narrow plate boundaries and stable plate interiors are so many orders of magnitude difference. You could see why plate tectonics is a great model. It gets more complicated with diffuse continental plate boundaries, but still that's orders of magnitude higher than the upper bound we put on stable plate interiors, as is oceanic thermal contraction and diffuse oceanic plate boundaries. Okay, so the final few slides of my talk, I'm going to talk a little bit about space geology. How much? -2. Oh, -2. Okay, I missed the signal. Okay, let's sum this up quickly. Okay, Jason told you about how all the work from 10, 20, 30 years ago showed how steady plate motion is. This is just an example of work Don Argus and I did almost 30 years ago, where we calculated the angular velocity between the Pacific plate and the North American plate. I think this was the first time it was done with space geodesy. It showed that not only the rate of rotation, but the pole of rotation we got from VLBI data was very close to what we got from marine geophysical data, Nouvelle 1A. Okay, so and then the last two, with the improvements of both data sets, we do see subtle differences between the two, though on average, plate motion is steady. If we look at mid-ocean ridges, we see slowdowns. Okay, we see slowdowns on these Arabia, Somalia, Eurasia, North America, Nubia, Somalia, Somalia, Antarctica, Nubia, Antarctica, Nazca, Antarctica, et cetera, and maybe small accelerations for India, Somalia, Antarctic Pacific, Australia, Antarctic, and Antarctic, the Sur plate, which I didn't even talk about. If we look at subduction zones, the well-known slowdown for Nazca, South America, for the Pacific Australia, Pacific North America, they're about the same. Looks like maybe Pacific Eurasia has sped up. And so I think we can just return to sum up here with this. And since I already read it once, I'll just leave it up for you since I'm over time. And thank you very much for your indulgence.